All right, so we're going to start with trigonometric functions today, but the first thing we'll do is go over some of the questions from the homework from last night. So number 18 on the homework was solving the equation 7 to the x plus 3 equals e to the x. All right, so we have base 7 on the left side and base e on the right side. And so we're in a situation here where we certainly can't get them both in terms of base 7, and writing it in logarithmic form is not going to be very helpful because we have exponential expressions on both sides of the equation. If we only had an exponential expression on one side or the other side, then we could just write it in logarithmic form, and usually that would work. So we can't do that, so instead what we're going to do is we're going to use a little trick where we take log of both sides of the equation. So log is a one-to-one function, right? We know that. And it's true that for any one-to-one function, you can apply it to both sides of the equation without changing the inequality, or the equation, or screwing up the equality or anything. So you can take any log you want, log base 10, ln, log base 2, log base 3. In this case, though, I would probably take log, or ln, I'd take natural log because we have base e on this side. So let's see what happens if I apply, if I apply natural log to both sides of this equation, right? On the right side, we know that natural log and e to the x are inverse functions, right? And what do inverse functions do when I compose them with each other? Yeah, they cancel each other out, exactly. So I end up with, and when I compose inverse functions, they cancel each other. I don't think we actually mentioned that, so I'm just going to throw this on the side here. So in general, if f of x and g of x are inverses, then by the inverse composition rule, f of g of x equals x and g of f of x equals x. So both of those things are true if they are inverses. So in this case we have ln of e of x, and so we get x. But that's the composition rule for inverses. That's a really important one we should know. Now, you're still saying, okay, well, we got all this crap over here. What do I do with this? Well, in this case right here, because we've taken ln of 7 to the x plus 3, I'm going to use the exponent rule for logs, and I'm going to take this x plus 3 out front here. So the x plus 3 can come out front since it's an exponent, and I'm just left with ln 7, right? And so now, to finish solving for x, what I'm going to do is I'm going to distribute the ln 7. ln 7 is just a number, by the way, at this point, right? Doesn't contain a variable, which is nice. So we get x ln 7 plus 3 ln 7, if I distribute, equals x. And so now I want to get all of my x's on one side of the equation. I'm going to put them on the left side here. And then I'm going to subtract the 3 ln 7 from both sides. And now, what do you think I should do so I only have one x? I collected all of my x terms on one side. Now what's the next step? So yes, what I can do is I can factor the x out here. Oops. And then I'm one step away from getting the answer. And the last thing to do is just to go ahead and just box this really quick, just so I don't write over it. And the last thing to do is just divide off the ln 7 minus 1, so we get that x equals negative 3 ln 7 over ln 7 minus 1. So, a little bit trickier. It involved using a couple different log properties and inverse function properties and some tricky algebra at the end here, but still not so bad when it's all said and done. So that's how we would approach that equation right there. Are there any other? All right, 13 from the homework. We're also going to take a look at. Number 13. We are given the function f of x equals 1 minus log base 5 of x minus 2. And we're asked to, first of all, find the domain of f, right? So the domain, right, essentially for log, when we're looking at square roots, we can't have negative numbers. When we're looking at fractions, we can't have 0 in the denominator. When we're looking at logarithmic functions, we can't have negative numbers in the log, right? That can't be true. So because logs, the domain of log is x has to, or whatever we're taking log of has to be greater than 0. So that means x minus 2. And it can't be 0 either, right? Log of 0 is also undefined, unlike square roots where square root of 0 is okay, but it just has to be 0 or bigger. This one just has to be bigger than 0. So x minus 2 has to be greater than 0, meaning that x has to be greater than 2. So the domain is all x such that x is greater than 2. Right. First of all. Secondly, if we want to graph f, we're going to use transformations based on what the original log function looks like. All right, so a couple things. What type of transformations do we have going on here? We have a shift to the right by 2. This is a reflection over the, what axis? Over the x-axis, yep. And then we're shifting it up by 1. So I like to do the reflection first. And so let's just go ahead and do this piece by piece. So imagine that I just reflected it. Right? If I just reflected it, it's still going to have the same x-intercept, but it's going to look like this. So just ln x would, or negative ln x would look like that, right? And so that's what the reflection looks like. Then all we have to do is we have to shift it up 1 and to the right by 2. So shifting it to the right by 2 is going to push it. I'm going to take this point right here, it's x-intercept, and I'm going to shift that over by 2 and up by 1, right? And then I know that's a point that it has to pass through. So I'm going to shift it over by 2. And up by 1, and so a new point that I know it has to pass through is right there. I know that the if I'm shifting it to the right by 2, my vertical asymptote used to be the x-axis or the y-axis, but now it has to be this line right here going through x equals 2. So that's going to be my new asymptote. It's going to have to go through this point. Its new x-intercept we can find by setting this equal to 0, right? And so we get, well, 1 is log base 5 of x minus 2 equal to 1. Write it in exponential form. And so we get x equals 7. So 7 is the new x-intercept. Let's see if we can get out there. 4, 5, 6, 7. So 7's way out there. And so it's going to look like this. Yep. Right, so that will be f of x right there. And this was just y equals negative ln x. I use that as sort of a starting point. Okay, what happens if I just flip it over the x-axis? Then I'll do my translations after that. And it sort of makes sense to do it in that order. All right. So, in addition, we're also asked to determine the range in any asymptotes of f. Well, the range is pretty simple. It's going to be all real numbers. It's still going to hit all values of y. Asymptotes, we have a vertical asymptote. And that is the line x equals 2, right? Find f inverse, the inverse of f. Probably not going to do the rest of it here. So let's go ahead, and we're essentially going to do all the same things for f inverse now for number 13 here. So on the next page, f of x is equal to 1 minus log base 5 of x minus 2. We're being asked to find the inverse, so let's just call f of x y. Let's swap y and x. And now we have to go ahead and solve for y. We have the inverse relation at this point. We just need to figure out what y is equal to. So what I'm going to do is I'm going to get log base 5 by itself on one side of x minus 2. And then I'll have 1 minus x on the other side. And then I'm going to go ahead and write it in exponential form. So 5 to the 1 minus x equals x minus 2. Whoops. I changed that from x to y. That should be y. And then lastly, y is equal to 5 to the 1 minus x plus 2. Not a surprise that the inverse function of log base 5 is an exponential function base 5, based on what we know about exponential and logarithmic functions, right? Use f inverse to find the range of f. So the domain of f inverse is the range of f, right? And so the domain of f inverse is what? Which I'm going to call it f inverse now. Yeah, it's all real numbers. It's an exponential function. So that's why, just by looking at f inverse, we can determine that the range of f is all real numbers. So we're doing the same thing twice, essentially. We already determined the range of f, but if you have f inverse, once again, the domain of f inverse is the range of f, right? So if you know the domain of f inverse, you also have the range of f. Lastly, they just want us to go ahead and graph this. Okay. So I'm going to use the same general idea. I'm going to start with an exponential function. What we have here, though, we could rewrite this actually as 5 to the negative 1 minus x. Oh, sorry, x minus 1, sorry. Now, what does the negative on the inside of the 5 to the negative x minus 1 do? What does the negative on the inside do? Negative on the outside is a reflection over the x-axis. What's the negative on the inside? The x minus 1 is a horizontal shift. What's the negative out front of the x minus 1 do?
Y-axis.
Yeah, reflection over the y-axis. So what I'm going to do is I'm just going to draw that reflection first, and then I'll translate the reflection to the right by 1, right? Translation to the right by 1 and then up by 2. But I find it helpful to draw the reflection first to know, and then just it's a matter of just pushing that around. All right, so I'm going to go ahead and draw the reflection, which is 5 to the negative x, which instead of going, if we reflect the exponential function normally sort of goes up like this, right? But if I reflect it over the y-axis, it's going to go down like this if I totally flip it over there. So it's going to look like, whoops. I wish I could make it intersect what I want to intersect. I'm just going to start. Let's try that again. One more time, just for good measure. There we go. So this would be the graph of y equals 5 to the negative x without the translations, right? So now we need to translate it to the right by 1 and up by 2. So if we're translating it up by 2, we had a horizontal asymptote of the x-axis. That new horizontal asymptote is going to be the line y equals 2, right? And so that's going to, initially, it's going to push the x-intercept up by 2, but then we have to push that over. So we know the point, we take this point and push it up by 2 and then push it over by 1. And we know it's got to go through this point now. And the question is, well, what is the new y-intercept? Because if I push it up by 2, I still have my y-intercept right here too. But then if I push it over by 1, that's actually going to make the y-intercept go up, right? Because of the profile of this curve. If I push it over, it's going to take this part and push it over, and so the y-intercept is going to go up by a little bit. So to figure out what the new y-intercept is, we can plug in what?
X is 0.
Yeah, we're going to plug in x is 0. So we get negative 0 minus 1 plus 2 out here. And so we'll end up getting 5 to the positive 1, which is just 5, plus 2 is 7. So the new intercept is now 7. So 1, 2, 3, 4, 5. I'm going to have to go ahead and make this a little bit taller. Let's go ahead and make this taller a little bit here. And we'll go up to 7. 1, 2, 3, 4, 5, 6, 7. And so the new intercept's going to be way up there because it curves up rather sharply. And so it's going to look roughly like that. All right, so there we go. That's a pretty bad drawing, but you get the idea. And this is what f inverse of x should look like. And we would notice that it should be a reflection around the line y equals x of our original function, which we knew sort of looked like this. All right, it looks, well, it's a reflection over the line y is equal to x for sure. All right, so that finishes number 13 from the homework. All right, so we did a quick little foray through inverse and exponential and logarithmic functions. Today we're going to get into trigonometric functions. Okay, so for those of you from who were in Algebra 2 this year, we did talk about trigonometric functions, but we're going to get into them in a lot more depth now than we did last year. But we're going to start off with what should be some review today, and then we'll sort of dive into some more advanced stuff in the next day or two here. And so today, essentially, first of all, make sure that you know the basic things about angles, right? You know what an angle is, and I'm going to talk about it as I work through some examples here, but know what it means for an angle to be in standard position, right, which allows us to have an angle within the coordinate plane, which allows us to have angles greater than 90 degrees, and it also allows us to have negative angles, right? So this gives us angles greater than 90 degrees and negative angles. Which are important. For trigonometric functions, also basic stuff you need to know is being able to convert from radians to degrees and from degrees back to radians, right? For radians, 2 pi is 1 full revolution, right? All right, so the unit circle is what we're going to be basing all of our trigonometry on for the first part here. And the unit circle, of course, is a circle of radius 1, right, with its center at the origin here. And we're going to be concerned with, the way this relates to trigonometry is we're going to be concerned with an angle, theta, right, which is going to relate to a distance traveled along the circle called t, right, which relates to whatever point the terminal side crosses the circle itself. So we have, by the way, standard position for an angle, right? Here's our initial side, terminal side, right? The angle, we open it up like that. And so the point where the terminal side crosses the unit circle, right, this point right here is going to be really important in terms of defining all of our trigonometric functions. And what's really interesting about the unit circle and really convenient about the unit circle is over here you see, first of all, arc length, the distance that we've traveled along the unit circle if we go an angle theta around the unit circle is equal to s, which is equal to theta r. If theta is in radians, this only works if it's in radians. If it's in degrees, we have to have a conversion factor there. But in the unit circle, r is always equal to 1. Right? If I make r equal to 1, that means s equals theta. That means this distance t right here that we've traveled along the unit circle is actually equal to theta, right? So we can almost think of the angle in terms of a distance, right? Which means that before we've defined our trigonometric functions in terms of angles, but we can also define our trigonometric functions in terms of distances, right? Which is just, and a distance is just a number, right? So it's a real number. And so we can think of it, we can essentially, divorce our understanding of trigonometry entirely from angles if we would like, and think of it just in terms of a number, right? Because a distance is just a number. In any case, we're going to define all of our trigonometric functions on the unit circle here to start, and then we'll see how that relates back to the right triangle definition that we're maybe more used to. But we're going to start doing it entirely based on the unit circle. And those definitions are as follows. So we're going to define, for instance, sine t, we're going to define sine t to be equal to the y coordinate, that the terminal side of the angle crosses the unit circle. So whatever the y coordinate at this point right here, that's what sine is equal to. Cosine is the x coordinate of the point where the terminal side crosses the unit circle. Tangent t is just going to be y over x, which shouldn't be surprising based on what we know about tangent in the past, and we'll see how that relates back to our right triangle definition later. But for now, tan t equals y over x. And then we have our three reciprocal trigonometric functions, which are just the reciprocals of the first two, or of the first three. So the reciprocal of sine we know is cosecant of t, and that's going to be equal to 1 over y. The reciprocal of cosine is going to be secant, and that's 1 over x. And lastly, the reciprocal of tan is cotangent of t, which is confusing. Maybe we'll put a little parentheses around them so it's not so confusing with the cotangent there. And that will give us x over y. So those are our 6 definitions of our trigonometric functions that we're going to use for now, right? And once again, at the end, we will relate them back to our right triangle trigonometry, but we're going to use the unit circle definition because it turns out the unit circle definition in a lot of ways is much simpler and easier to work with than our right triangle definition, especially when we're dealing with angles that are bigger than 90 degrees, angles that end up in the second quadrant or the third quadrant, or angles that are negative. And by the way, just so we're clear, this is the first quadrant, second quadrant, third quadrant, and our fourth quadrant, right? We should know our quadrants for sure here. Okay, so let's say let t be a distance traveled along the unit circle. Starting on the initial side, or the initial side, right? And the points that we end up at the point that you get to after traveling t along the unit circle is negative 1/2 square root of 3 over 2. Right. Go ahead and find the values of all 6 trig functions. So visually, what does this look like? So here's my unit circle. And so the point negative 1/2, so let's go ahead and draw my unit circle, sorry. The point negative 1/2 square root of 3 over 2. So that puts me in what quadrant? if x is -1/2, and then we have square root of 3 over 2.
Second.
Second. So we're somewhere, assuming we started here, right? And then we traveled along the unit circle, and we end up somewhere over here, right, in the second quadrant. Right, so this is the amount t that I've gone, right? Right, so, and this point here is -1/2 square root of 3 over 2. Okay, so if that's the case, and of course there's an angle theta, right? There's an angle theta that will correspond to that. Ah, crap. Oh, great. All right, sorry, let me just finish fixing this here. All right, so there's an angle theta that will correspond to that angle. And so we can just use our definitions of our trig functions to figure out what the trigonometric functions are for that angle. So sine of t will be equal to what? It's just equal to this square root of 3 over 2, right? Cosine of t is going to be equal to the x-coordinate, which is -1/2. And then tangent t is going to be equal to y over x, right? So square root of 3 over 2 divided by -1/2. Right? Which will end up, if we multiply that out, that'll just give us negative square root of 3, right? Because we'll multiply by -2. It's the same as dividing by -1/2. So then the reciprocal of sine is cosecant t. That's going to be 2 over square root of 3, which if you rationalize the denominator becomes 2 square root of 3 over 3. Secant t is going to be equal to, well, the reciprocal of -1/2 is -2, right? And cotangent t is going to be -1 over square root of 3, which if I rationalize the denominator becomes negative square root of 3 over 3. And get in the habit of rationalizing the denominator of all of your trigonometric values, because then it's much easier to compare them if we do that. Okay, so if we're actually given the point that we end up on the unit circle after traveling t along the unit circle, then it's a pretty easy process of just applying the definitions to find the values of the 6 trigonometric functions. It becomes a little bit more difficult when we're actually given the value t that we're, and not the value of the point itself, which we'll investigate in a second here. All right, so if we're given the point along the unit circle, it's really easy to determine where we end up along the unit circle. And we also know that with the unit circle, it's easy to determine what the trigonometric functions are. But if we're just given the distance that we've traveled along the unit circle or the angle that corresponds to that, then it becomes a bit more difficult. All right, so let's start off with some of the quadrantal angles here. Let's say, so first of all, quadrantal angles, just to review. Are 0, 90, anytime we end up on one of the quadrant boundaries, right? 0, 90, 180, 270, 360, and any multiple of those, right? So those are my quadrantal angles. And so even though t, we think of it sort of as a distance, we can also think of t as an angle, of course, because there's an angle. If we open the angle up, that point where the angle crosses the unit circle corresponds to that distance t. So we know that for the unit circle, theta is equal to t, right? So I can either take sine theta or sine t, it doesn't matter. So if I were asked to find, let's say, the values of the 6 trig functions of theta is equal to 0 degrees, right? Meaning, in terms of the unit circle, right? Here's my unit circle. I'm traveling 0 degrees, meaning I'm ending up exactly where I started. The terminal side and the initial side of the angle are the same. So, but once again, we don't have to worry about triangles or anything like that because we're just concerned about the point along the unit circle, which, because the unit circle, we know the point that it gets to is what? Or that it's at. What point is that? 1, 0, right? 0.10. Right, and so sine of 0 is equal to 0, the y-coordinate. Cosine of 0 is equal to 1. Tangent of 0 is equal to y over x. 0 divided by 1 is 0. Now, cosecant of 0, on the other hand, is equal to 1 over 0, which is that, what's up with that?
Fine.
Yeah, it's undefined. So sometimes the trig functions are undefined, and they're undefined for some of the quadrantal angles. Secant of 0 is 1 over 1. That's just 1, which is fine. And cotangent 0, well, that's also 1 over 0, so that's also going to be undefined, right? And we could do the same thing for any of the other quadrantal angles. So let's say, instead of looking at the angle 0 degrees, which ends at that point right there, let's say find all 6 trig functions for theta is equal to, let's say, 270, right? So in the unit circle, that's also a quadrantal angle. If here's my unit circle, if we go 270, we end up right there, right? So my angle would sort of look like this. My angle theta would look like... sort of like that. I'm not even gonna. All right, so, if we end up at this point right here, this point is the point 0, -1, right? And so that's where we would end up if we rotated 270 degrees. So in any case, if we go sine, Mr. Burke? All right, so sine of 270 is just going to be equal to the y-coordinate. Cosine of 270 is equal to the x-coordinate. Tan 270 will be equal to the y over the x-coordinate. And so in this case, we're dividing by 0, so tan of 270 is going to be undefined. Cosecant 270 is going to be the reciprocal of -1, which is also -1. Sine 270, sorry, not sine, secant. Secant 270 is the reciprocal of cosine, which is going to be undefined. And then cotangent of 270 will actually be 0 over -1, so it will be defined. Okay, so for a quadrantal angle, it's really easy if you use the unit circle to determine all of the trigonometric functions that correspond to that quadrantal angle. And of course, any angle that ends up on one of the quadrants, so let's say I had an angle like, let's say an angle such as like 3 pi, which is, way out there, right? Where am I going to end up if I go 3 pi? Well, here's my unit circle. If I rotate 3 pi, I'm going to end up 2 pi will give me here, 3 pi will bring me all the way over here, and so the point that my terminal side will intersect my unit circle will be -1, 0. So, once again, for any angle that ends up on one of the axes, we can always easily determine the value of our trigonometric functions. So, if it's a quadrantal angle, we can easily determine the exact value of the trigonometric functions. Angle, then that would mean it would correspond to one of the special right triangles. Let's review those really quickly. All right, so we have our special right triangles here. So we have our 45, 90 right triangle, where if, let's say the two legs, the congruent sides are 1, what would the hypotenuse be? And in our other type of triangle, our 30, 60, 90, so we are 30, 60, 90 right triangle. If the short side is 1, the hypotenuse is always twice the length of the short side. Yep, and the intermediate, the middle side, is square root of 3. All right. So using what we know about our special right triangles, we can determine what our unit circle values happen to be. Okay. And so, for instance, if I ask you to find the 6 trig functions for 45 degrees, let's say. If we go ahead and draw our unit circle, and we'll start our terminal side here, and then we'll open up to, start our initial side and open up to our terminal side. Here's our 45-degree angle. Actually, I'm going to need that space. What we find here is that we end up between the point that it crosses the unit circle, this point right here that we're trying to figure out, right? We form a right triangle, essentially. If I draw a line, a vertical line directly down from that point to the x-axis, we form a right triangle. And if the hypotenuse of our right triangle, it is 1 in this case, it has to be, because it's a unit circle, it has a radius of 1. And so what do our other two sides have to be, if that's the case? Right? If the hypotenuse is 1, so going in reverse from this model right here, if the hypotenuse is 1, what do the lengths of the sides have to be?
Square root of 2 over 2.
Yeah, 1 over square root of 2, which is equal to square root of 2 over 2 when I rationalize the denominator, right? And the same thing is going to be true for the other side, also going to be square root of 2 over 2, right? So our y, we found the lengths of the sides of those triangles, and those sides, because it's a right triangle, correspond to the x and the y coordinates at this point, right? So we know now at this point, this distance right here is the x coordinate of this point, because it's along the x-axis, right? So this distance right here is the x coordinate, and this distance right here is the y coordinate of the point. So they're both going to be square root of 2 over 2, right? And so that means sine 45 is square root of 2 over 2. Cosine 45 is square root of 2 over 2. Tangent 45 is just square root of 2 over 2 divided by square root of 2 over 2, right, is going to be 1, right? Cosecant 45 is going to be the reciprocal of square root of 2 over 2, right? Go ahead and erase this here. So it's the reciprocal of square root of 2 over 2 is 2 over square root of 2, which if I rationalize the denominator ends up becoming just square root of 2, right? And that means that so is secant of 45 is also going to be just square root of 2. And cotangent 45 is just the reciprocal of 1, which is also 1. Right. And so, and any angle that ends up having what we're going to call a reference angle of 45 is going to have this same situation. So no matter where we end up, we can always form, no matter which quadrant we end up in with our angle, we can always form a reference triangle. Let's say I had an angle that ended up over here. We could form a reference triangle between the terminal side and the x-axis, right? And that triangle, we can use the dimensions of that triangle to figure out the x and y coordinates of whatever point we end up with along the unit circle here. And so between the reference triangle and the angle, we can determine what those points are if it's a special angle of some sort. All right, so using the same reason, why don't you go ahead and find all 6 trig functions for theta equals, let's say 240 degrees. So go ahead and draw the angle, draw your unit circle, draw the angle, indicate the point that you would end up on the unit circle, and use what you know about special right triangles to determine the coordinates of that point on the unit circle. So if we're trying to find these 6 trig functions for theta equals 240, we got to go ahead here and draw our unit circle. Start on our initial side, open up to 240 degrees. Right, and so this point on the unit circle is what we are striving to find here. And so we once again see that it forms a right triangle between the x-axis and the terminal side. We can always form a right triangle like that, and this right triangle is going to have this angle right here is going to be 240 minus 180, which is 60 degrees. So this triangle ends up being a 30, 60, 90 right triangle. And so we can use what we know about it to determine the lengths of their sides. We know the hypotenuse, of course, is always 1 for any of these right triangles that we make in the unit circle. What is the length of the short side going to be if the hypotenuse is 1?
1 over 2.
And that means the length of the long side is?
Square root of 3 over 2.
Yep, square root of 3 over 2.
Square root of 3.
Yes, it's square root of 3 over, well, the length of the side of the triangle is square root of 3 over 2, but the coordinate, of course. And so the coordinate that we're concerned with here, it's below the x-axis, so of course the y-coordinate has to be negative, and this distance is square root of 3 over 2, so the y-coordinate is going to be negative square root of 3 over 2. And the x-coordinate is going to be, well, the x-coordinate should also be negative, so it's going to be negative 1/2. It's going to correspond to the length of this side. It's going to be the x-coordinate at that point. So negative 1/2 and negative square root of 3 over 2. And so sine 240 is just going to be equal to negative square root of 3 over 2. Cosine 240 will be negative 1/2. And then tangent of 240 is the quotient of those two. Negative square root of 3 over 2 divided by negative 1/2, which will give us square root of 3. Cosecant 240 will be the reciprocal of negative square root of 3 over 2, which is negative 2 over square root of 3, which becomes negative 2 square root of 3 over 3 if we rationalize the denominator. Secant of 240 will just be negative 2, and cotangent 240 will be 1 over square root of 3, which, if we rationalize the denominator, becomes square root of 3 over 3. So it's pretty easy using the unit circle. If I have a special, if I have an angle that results in forming a triangle, a right triangle that has special angles like 30, 60, or 45, then I can use what I know about those special right triangles to determine the points, the point that the terminal side crosses the unit circle, which of course corresponds directly to all of my trigonometric functions. So if we see an angle, so any angle, and of course, once again, we call the angle that is formed between the x-axis and the unit circle, sorry, the x-axis and the terminal side, the reference angle. Right, so the angle formed between the x-axis and the x-axis and the terminal side of the angle is the reference angle. So any angle with a reference angle of with a reference angle that is a special right triangle, that's a special angle, sorry, or a quadrantal angle can be found exactly. We can find exact values of those, right? So any angle with a reference angle that is a special angle or a quadrantal angle can be found exactly. Of course, not all angles have angles or quadrantal angles as their reference angles. So for instance, if I asked you to find like cosine of 23 or cosecant of 42 degrees, or maybe cotangent of pi over 12, you would have to use your calculator. None of those, of course, are special angles or quadrantal angles, right? And so we're going to use our calculator. And with the calculator, it's important that you are in the right mode. Right? If you're using, for these first two, you need to be in degree mode, right? You must be in degree mode for these first two. To be able to calculate them, you must be in radian mode to calculate this one, because pi over 12 is a radian measure of an angle. All right? So for the first one here, cosine of 23, I am in degree mode, and I end up getting that cosine of 23 is equal to 0.92, and I'll go out to 3 decimal places, 1. For cosecant 42, there's no cosecant button on our calculator, as you'll notice. So what we have to do is we know cosecant is the reciprocal of sine, so it should be the same as the reciprocal of sine 42, right? So that's what we're going to plug into our calculator, 1 divided by sine 42, and we'll get 1.494. And then for this last one, for cotangent, that's the reciprocal of tangent, right? So I'm going to have to type in 1 over tan pi over 12 after I've put it into radian mode. So hit mode, make sure you are in radian mode, and then do 1 over tan of pi over 12. And you'll get 3.732. Okay. So for non-special or quadrantal angles, we must use our calculator. Okay, now the last we want to tackle today is finding trig functions for points on circles whose radius is not 1. Right, so if we don't have if we have a point that's not on the unit circle, but we still want to figure out the trigonometric functions of the angle whose terminal side passes through that point, then we need to develop some new formulas that are going to work for, and they're going to be based on the unit circle formulas, and we're just going to sort of expand them from the unit circle formulas. But it's going to be important to be able to find those values as well. So, let's say we want to find, well, actually, let's go ahead and derive this really quickly. So let's say here is our axis, and let's say here is, first of all, our unit circle, and then we have some other circle of indeterminate radius, but not 1 though. So this is radius 1, and the radius of the bigger circle is just going to be r, right? Now, if we draw our triangles here, right, and I'm going to try and so this point will be the point xy. So let's say we have some point along the unit circle, or sorry, along a circle that is not the unit circle, and we want to figure out what the trigonometric functions are for that angle that ends up at that point. Now let's say this corresponding point in the unit circle is going to be x star, y star, right? Okay. Now, and then of course this will be angle theta, right? So sine theta, whoops. Right, sorry. Oopsie daisy. So sine theta is going to be equal to y star, which is the same as y star over 1, right? If I divide something by 1, I haven't changed it, right? So sine theta we know is equal to the y coordinate of the unit circle, which in this case is y star. Now, because these two triangles here, these two right triangles, have the same angle, right? Have all the same angles. So by angle, they're similar, meaning that the ratios of their sides are going to be the same. So y star over 1 has to be equal to, let me use the same color here, y star over 1 has to be equal to y over r, right? By similar right triangles, right? Which makes sense. This divided by this has to be equal to this divided by this because the two triangles are similar, right? Similar triangles have to have ratios that are the same. So that means sine theta is equal to y over r, right? So, and the same reasoning can be used for cosine and tangent. So cosine theta is going to be x star over 1, right? It's cosine theta is x star, but I can also write it as x star over 1. I know that x star over 1 has to be equal to x over r by similar triangles. And lastly, tangent theta, right? Tangent theta has to be equal to, well, we know it's equal to y star over x star, and once again, y over x has to be equal to y star over x star has to be equal to y over x by similar right triangles as well. So the tangent definition doesn't really change, but these are all of our new definitions for sine, cosine, and tangent if it's a point on a circle that's not a unit circle, and that's the proof, right? And of course, similarly, cosecant theta has to be r over y. Secant theta is the reciprocal of cosine, which is r over x, and cotangent theta is going to be equal to x over y. So cotangent and tangent are pretty much the same, but sine and cosine now involve r if r is not 1. Okay, and that's proven by this, the similar right triangles that we have here. Now that we've done that, let's go ahead and I'm going to have you do one last example before we call it quits today. Find the 6 trig functions for an angle theta whose terminal side passes through the point, the point 4, -3. Take a crack at that. All right, let's give this a shot here. So let's go ahead. I always like to draw a diagram. So my point is 4, -3. So 1, 2, 3, 4, and then 1, 2, 3. So this point right here. And so imagine that this is a point along a circle of some radius here. Right. And so there's the terminal side of my angle, here's the initial side of my angle, here's theta, right? And so there's the point 4, -3. And of course, we can always form a right triangle between the terminal side and the x-axis, drawing a vertical line like so. And so that side is 3, this side is 4, right? Because the coordinates are 4 and -3. And the thing is, we need to know r for our, if the unit circle is not being used, we need to know what the r is. So the radius of the circle happens to be. So that would be this length right here, which we can find through Pythagorean theorem, right? So 4 squared plus 3 squared has to equal r squared. So r is going to be equal to the square root of 16 plus 9, which is 25. So r is 5, right? And so sine of theta is going to be y over r, which is going to be 3/5. Cosine theta is x over r, which is 4/5. Tangent theta is going to be y over x 3/4. Cosecant theta is going to be 5/3. Secant theta is going to be 5/4, and cotangent theta will be 4/3. Those are all your reciprocal functions. All right, so you see it's not so difficult. We just have to incorporate r if r is not 1. If we're not using the unit circle, so slightly trickier, but we can still do it and get all of the 6 trigonometric functions if we know the point that it passes through. So that's it for today. The homework for tonight will be as follows. So the homework for tonight is on the new handout that I've emailed out to everyone today. Also included with the handout, I have attached solutions to the odd numbered questions, because I had been assigning the odd numbered questions because the answers to all the odds are in the back of the book. But it didn't occur to me that, for some reason, that your book, being a newer edition, has different answers because there's different questions, because they always change the problem sets on those. So I'm going to start including the solutions to all the odd questions at the end of all the handouts so that you have more feedback. In addition, I will have the Chapter 4 test that we'll use for the Chapter 4 assessment out today. I'll email that out to you as well as the handout for the homework today, and the solutions to that will be coming out in the next day or two. All right, have a great day.